This is the so-called reluctance bus alternator. As I've noted, this part here is a gear-driven field rotor. We'll turn that around. We'll also turn this around. That gear rotor goes in between, that gear-powered rotor goes in between the field and the stator, so that the only moving part is the field rotor. We'll turn these parts around. Extremely heavy machinery. So there we can see the gear, the field poles with a hollow section in between. In order for these field poles to rotate, there's not an axle going through the entire thing. It's held together by brass. I have some other pictures showing how that casting is made. You ought to be able to see that brass ring holding two opposite pole faces together. And this is the AC rectification that the bus alternator makes through the use of 3 diodes. And at that point we're going to go and show the modification that Magnetek of Akron, Ohio made. These diodes, by the way, are oil circulated for cooling. They also have metal. And this housing part goes over that, and it's got an oil port for circulation of oil through there, and there's where the DC posts go through on the outer housing. And like I said, again, we got pictures of all that. Okay, now the modification that Magnetek of Akron, Ohio did, if I can get in through here, is they took out the entire diode assembly.
You blew it up?
I'm doing something.
I thought you blew it.
There's the modification that Magnetek of Akron, Ohio, when they had a factory there, made. And what they did there was they changed that DC output back into 3 isolated phases. And right now we have them wired in Y to obtain a higher voltage on one side. And we also have a variable speed motor, a Leeson drive, powering the whole thing, so that we can run this at any RPM that we want, up to 120 Hertz. It's set at 20 Hertz where we're going to do this experiment. And we're also going to show modification that the Solax Automotive Specialties out of Manway, Ohio did. They attached they removed the gear and put a pulley in between 2 of these devices. And oh geez, we have to turn that back light on. Pardon us, folks. And there's the modification, if we can see it. We got voltage meters on each side. When we turn it on, we'll be able to see the voltages being procured from each side, and the meter in the middle will show the total voltage. We have these 2 sides wired in Y, also in series. Try to get a backlight on here. Yeah, I'll try to get this done quickly. Already wasted 5 minutes. What we're going to do here is do an experiment on remnant magnetism. And what I've noted before, and I'll quickly read that out. For the example of an actual energized rotating electromagnet being used as the field rotor in an alternator, relatively speaking, reversing the rotation of the field rotor should have the same effect as instead keeping the same rotation and reversing the direction of the direct current going through the field rotor. If this does not occur, it implies that other external factors are in play. Nevertheless, the fact that the spin of a ferromagnetic material creates its own magnetism should be indisputable. Whether in fact this magnetism is remembered in the material, then we may call that effect remnant magnetism. The following test should show this thesis. Show the voltage obtained without any field current input. Show the voltage attained with a field input. Stop the rotation and reverse it and show the new voltage with the same field amperage. And now apply the relativistic equality. Go back to the original direction of rotation and instead reverse the field. We also have some technical problems with the device. The belt and the pulley aren't lining up real good on the installation. And here we have the rotor itself. And it needs to come towards this direction. We can't really see this on the camera. But we'll go ahead and turn our meters on and start it up and show that what's obtained without any field magnetism. We have a variac also. These tests are going to be done at a 2-volt input to the field. The resistance of the field is about 1.3 ohms on each side, 2.6 ohms total in series. And that goes to a step-down transformer and a set of diodes. And then from the diodes it goes up in the preferred direction that we're going to show. There's a red wire and the yellow wire connecting to the black one, which when we connect, that would connect the field. So go ahead and start it up. And we'll show the Gleason variable control. And we have it set for 20 Hertz. Now, since there's 6 segments on the pole face rotor, 20 Hertz will give us about 60 Hertz on the bus alternator output. Go and turn our voltage meters on. Got 0.29 volts in the front, 0.18, 19 in the back, and 0.47 volts on the total series, showing that each side's in phase. The voltages are adding to unity. One of the problems with this is that one side produces more than the other side, and we won't go into that story why that is. Essentially, Magnetek messed up when they did the alteration, and when it was corrected, it came out like this. We'll go ahead and turn the field on. It's set at 10 volts. And after it goes through that 4-to-1 step-down transformer, that'll be about 2.5 volts in the field. It doesn't produce much at this somewhat low RPM. We'll connect the field, show that.
Christ.
Quits.